So let me again have quick, intro. It was all echoing. So we have Dr. Filippo Capolino from University of California, Irvine. He's a well-known expert in applied electromagnetics, metasurfaces, antenna area. He's associated with my group here also. Two of the students are sitting here, those we are working together. And we know each other for last 16, 17 years at least. And not only we are good colleagues, we are good friends also. The point that brings him here, because he's also the JTP director of the CSRC program from the University of California, Irvine side. It is his first visit to SDSU, and you'll listen from his talk that there's a lot of plethora of information to learn and lots of knowledge he has that he can pass to us. With that, please.
Thank you, Mr. Satish. So it's my first time here at San Diego State University, and it's a beautiful campus. And I'm happy that I'm now the director from UCI joined the degree program. And so I came here also to talk to some of the faculty members, et cetera, and I guess I will be here again because it's not really so far away from UCI. It's actually only 1 hour and 15 minutes drive. So I wanted to talk about, besides my role as a director of this JDP program, I want to talk about this beautiful research topic. I've been working on this topic for the past several years, and I hope to find collaborators here to continue to study this topic. It's a very broad area of research, really broad, and there is still a lot to do. Okay, it's complicated to understand, and you can see this topic from various angles. So we show a few angles, but maybe some of you will have also new ideas, etc., etc. Okay, so of course I have to acknowledge the list of collaborators below. Here, let me put the pointer on. There's a pointer. So these are the students that have been working on these topics and are now graduated. Some of them are here in San Diego, working in some companies. These are the list of collaborators. Professor Pigotti is a mathematician. Professor Green is in electronics, IC design. Professor Boirazzi is in optoelectronics. This student is a student of Professor Boirazzi. And then these are current students working on this topic. And these are the findings of this topic. Anyway, so there are various, this is a list of topics I'm going to discuss today. Okay. So the first one is, what is an exceptional form? Okay. It's not really a common topic. And so usually people don't know what it is. And I'm still trying to understand what it is also myself. So I'm going to give you a few explanation of this concept. So consider you have a system made of two subsystems, two resonators, two springs, or below you have a circuit analog, two LC resonators which are coupled. So usually if you have one resonator, you have a resonant frequency, you couple two resonators, you have two resonant frequencies, right? And so this would be the time domain signal or whatever observable you decide to look at. And this is the complex plane representing eigenvalues. You can have, for example, an eigenvalue here, an eigenvalue here. These are resonant frequencies. Okay, omega are the resonant frequencies. And these are separated, right? And so in time domain, you have this beating between two resonant frequencies that will give you this kind of modulation. So the question is, can you have these two poles of what? When you represent the system, you can see these natural responses in terms of poles, okay? So the answer is yes, you can put them together, you can overlap these two poles. But you need to have something special in the system, otherwise there are fundamental theorems that prevent that. So for example, this is one of a strategy this is a strategy called the PT symmetry, parity time symmetry. In that case, you can put the two poles on top of each other. Parity times P means is a parity symmetry operator, means a mirror symmetry operator. You can see left and right, LNC, you have the same LNC on both sides, right? But also you have, what happens if you mirror the resistance on this side, you would have a resistance on this side, if you mirror, right? If you apply the symmetry operator. But then we apply the time reversal operator, the T operator. So whatever is L remains L, whatever is C remains C, but R becomes minus R, because if you reverse the R of time, if something is decaying exponentially, it becomes growing exponentially. So it becomes gain. So when you apply then this kind of two mirrors, R and minus R again switched when you apply the time symmetry operator. And so you get back the same identical system. Okay. So this system is said to satisfy PT symmetry. And so in that case, you can, I don't say it's always the case, but for some choice, particular choice of parameters, you have these two resonant frequencies, these two eigenvalues of the system on top of each other. Okay. So DPD are exceptional point of degeneracy, points in parameter space where the system has degenerate eigenvalues and eigenvectors. Actually, there are many systems that have degenerate eigenvalues, but not degenerate eigenvectors. What is an eigenvector here? When basically is a polarization state of this system. Or if I choose a system, if I choose a state vector to describe this system, okay, so that would be when you have a rational system, the eigenvector, the vector that describes my system is called the eigenvector. So at the exceptional points, two eigenvectors are coalesced. They have coalesced as well. Okay, so why EPD? It's an exceptional, so it doesn't happen in any system. Usually is a point, so it happens only for specific set of system parameters. So it's a point in parameter space. And D for me is the most important, is the degeneracy condition. Traditionally, these points have been called exceptional point thanks to the mathematician Cato, who studied perturbation theory of systems. He was a professor in Berkeley who wrote a very famous book in the 60s. And so Cato called them exceptional point, but I like to call them degeneracy conditions. Indeed, for me, even point can be neglected. I will call them exceptional degeneracy points. Okay. D for me is a key point because I want to look at the physics of what's happening. So there are a lot of applications. The most important one taken by the community is in sensing. Okay, here you have two examples. Sensing, basically, you can see here, this is a sensor based on two coupled LC resonators. This was published in National Electronics 4 years ago. There is a catch. This actually, in my opinion, is not working. Actually, it's not only my opinion, because anyway, when they want to keep PT symmetry, remember PT symmetry, they want to keep this PT symmetry to observe the two real eigenvalues, the two real resonant frequency of the system. So they want to measure something changing the capacitor. Most of the sensors are done like that. You have a sensing capacitor. When you sense something, the capacitance changes, and then you want to detect the shifted frequency of your resonator. But they want to keep PT symmetry, so they shift this one using a variator. This is a particular example. But if you don't know how much this is changing a priori, because that's what you want to measure, how can you change this of the same amount of value? Well, that's the catch of this paper. So this paper is just good to represent the concept. It's not really a sensor, but we have solved this problem. Okay. So sensing challenges in sensitivity, robustness, sensing range, accuracy. This idea, which is basically fundamental physics, is used to solve the first one. Okay. This idea was already proposed in the past. These are the first experimental demonstrations. Okay, they use this system here. How do you study this system? So this is a very general approach. M is a matrix, it's called the system matrix. In some cases, could be the Hamiltonian. matrix when you want to represent the energy levels of a system. It doesn't need to be a Hamiltonian, it can be just a matrix representing the evolution of a system when you look at the system from Ada's point of view. But if you come from physics, you can see this M as the Hamiltonian. And this is a variation, the variation of your state vector. Okay, so you describe the system with this multidimensional first-order differential equation. It's linear for the moment. Okay, C is a state vector, so it depends on how many variables you choose to describe the system. Then let's assume you will want to look for solutions of this kind. So where omega would be the oscillation frequency, and then this becomes that. So you can say this becomes an eigenvalue problem, linear. Okay, so basically you can solve these. The eigenvalues will be j omega, and the eigenvectors will be the state, the eigenstates, the eigenvectors, representing. So in this circuit, it would be representing the circuit and the voltages associated to the resonance. Okay, so nothing new here. What is very important is that when you have this exceptional point, let's assume omega E is a resonance solution of the system. Forget about this. This is much more general, can be applied to any system. Let's assume omega E is a degenerate solution of this system. Then when I perturb my system, it means that your matrix M has some perturbation somewhere. Okay, and let's assume epsilon is a perturbation of your system. So when you work at exceptional point, the eigenvalues or the resonances of your system are perturbed according to this formula. This is the first order approximation. So the perturbation of your resonant frequencies are not just proportional to epsilon, they're proportional to the square root of epsilon. It's the key point. So, have you ever seen in physics a case where a perturbation is not described by the Taylor expansion? Pretty sure you haven't. This is not a Taylor expansion. So this is called Puiseux series expansion or fractional power expansion. Is a key property of a perturbation of exception. Okay. Puiseux was a French mathematician who lived a long time ago. Okay, so he is the first one who understood that you can expand. He applied the theory to perturbation of a solution of differential equations. Okay. So yeah, please interrupt me anytime you want.
The epsilon is the perturbation that you need to the entries of the matrix M.
Yes, is a perturbation to the system which is reflected to a perturbation to at least one element of a matrix. Okay.
And if you're not at one of these funky points, then the perturbation on the eigenvalues will be coming
proportional to epsilon, linearly proportional to epsilon. It's proportional to the square root of epsilon only if you perturb your degenerate eigenvalue. This was also in Cato's book, the famous Cato's book written in 1966. So let's take this simple generator. This is PT symmetry. 99.99% of the papers about exceptional point are about PT symmetry, what I told you before. So you have some symmetry. But the exceptional point is much more general topic than PT symmetry. So let's consider this system. This will be the matrix associated to that system. These are the resonant frequencies. You can see that if I want to make omega 1 equal to omega 2, I need to have this B equal to 0. So if I have B equal to 0, I'm going to have omega 1, omega 2 equal to each other.
What is B?
B in, is a combination of the parameters of a system. So if you want to assume, if you want to build an exceptional point, you set B equal to 0. When B is equal to 0, for example, here we vary G. Okay, G is this parameter. I guess this is, you don't need to be an electrical engineer to understand this circuit, right? It's just the very basic circuit. This is a transformer, and G is a resistance or a gain in this case. So for one and only one value of this G, you have this point, which is a bifurcation point. Here we plot the real part of the resonant frequency. Here we plot the imaginary part of the resonant frequency. And you see at that point, these two solutions merge. they become 1, they're coalescence. In that case, B is equal to 0. So for that value of G, B is equal to 0. I told you the exceptional point is not just when two eigenvalues are identical to each other, it's when the two eigenvectors are identical to each other. Well, I'm not showing you that here, but at that point also the two eigenvectors are equal to each other. Okay. So what happens when you have innate electronics? When you have gain, you always have some nonlinear phenomena associated to that. Does gain without nonlinearity doesn't exist? Think about the laser. A laser works because you reach a saturation effect. So nonlinearity is important. So here, this will be the nonlinear case, which is a realistic description of some active components. It follows a cubic law. It's just an example. That's you can apply this to other system with different nonlinearities. And what happens? We make the system a little bit unstable, so we make an oscillator. So now we let the system to be unstable. People usually avoid to make this unstable. So everybody trying to make sensors, not everybody, almost everybody, want to work in the linear regime. Here we actually say, let it be unstable. So what happens to a system most of the time when it's stable becomes an oscillator. Okay. So indeed, there's an oscillation frequency, there's a spectrum, it's pretty clean. And interesting, it oscillates at exceptional point frequency. By the way, it's almost always the case. We didn't know that at the beginning. Okay, now what happens if you apply perturbation to the nonlinear system? This is really interesting. Well, these blue curves represent the perturbation around the capacitance value of C2 that will give you the exceptional point. When we perturb this capacitance C2 around the value that will give you the exceptional point, you have this bifurcation. Now, since we don't satisfy PT symmetry anymore, you have a bifurcation on both sides of the variation. You have two real frequency. I mean, you have two real parts, but also you have two imaginary parts. So you can see the system is always unstable. People want to avoid this, but actually, that's what we like. That's what we want. Actually, we submitted a patent on that, okay, because I think it's a great discovery. Now we let it oscillate thanks to the instability. And now, if we follow the variation of the oscillation frequency on the unstable circuit, it follows this interesting shape. This extremely large variation of the oscillation frequency or very, very tiny variation of the capacitance. So this is really extremely sensitive to a variation of a capacitor. So this is a good sensor, extremely sensitive sensor. When you change something around this point, look how strong is the sensitivity. Sensitivity is associated to the slope around this point of this curve dot. So basically, it's a sensor. We're not afraid of instability. Actually, we use them. And there is a lot of dynamics that we don't understand. But if you neglect for the moment the nonlinearity, the perturbation of a resonant frequency follows this value here. You see the square root I was mentioning before of the variation of a capacitor. So let's assume you have a variation of a capacitor of 1%. How much is the square root of 1%? It's 10%. So you see that now the frequency is changing 10%, while my variation was 1%. I amplify by an order of magnitude the effect of the perturbation that is visible by just observing an oscillation frequency. So this experiment we verified. We applied this also to two coupled transmission lines. Here we make an oscillator. Anyway, the same phenomenon. This is a very general concept. And we are now trying to apply these to lasers. Okay. Anyway, so the sensing application is one of the main ones for exceptional points. There are many things that are important when you make a sensor. I'm not claiming that we solve all the problems. We just provide some electronics that is very sensitive. Of course, there is a selectivity problem that usually is done by chemistry or by some other things when you have a real sensor. These are another very interesting things. We also have a patent on that. So let's take this was our discovery. So people use two resonators joined together to make an exceptional point. The two resonator concept is very general. Forget about LC. Look at the mathematical description. This is very general. So the system matrix, we just make time modulated, periodic in time. At least one parameter of that matrix oscillates in time. Okay. Now, how do you study this problem? Well, we build a state transition matrix, which is just the exponential function of m and Pm, the period. And then we look at this state. So we look how the state vector changes from one period to another period. And now this is the matrix that we want to find degenerate. Okay. Indeed, we find it. I'm skipping the details. We have a paper that explains the details. Anyway, there are eigenvalues that are degenerate for that case. We also did the experimental verification, and then we found that, look, in the experiment, the splitting of the resonant frequency of my single resonator splits in two frequencies. It's a single resonator. Usually, when you shift the frequency, you have one frequency that moves. Here, when we perturb the system, we have a split and we have two frequencies, thanks to this time modulation. And you can see that even the experiment follow this Poinsot series expansion. Delta is the perturbation, and F is the shift. And you see, and you have two indices, 1 and 2. These are the two frequencies. And we can follow how they separate from each other away. So here the frequencies are not degenerate anymore. We just perturb the system away from degeneracy condition. This is a way how to apply to biosensors, etc. Okay. So the idea, this was for me a very important paper, not for me actually, for many people. This was 8 years ago, was published in Science. This was published by some physicists, Professor Christodoulides, Professor Kechabakan. They were at Creole in Florida. This is a college of optical sciences. They basically, this is what's important. They are looking at the resonance, the lasing frequency of two rings. One has losses, one has gain. And look, compare it to the lasing frequencies of a single ring. You can see a single ring may have several lasing frequencies. Now, if you have two couple rings, each of these lasing frequencies splits into, it's normal when you couple two oscillators, you have splitting of the frequencies. But instead of having, now we couple the two, but one has lost symmetric, anti-symmetric with respect to the gain. And you have one single resonant frequency. Incredible, right? So this was a very important paper at that time. So I talk about two couple resonators. So I've been talking about this. We look at the function of, this is how the system varies in time following this. We have a resonant condition. It means the two modes of the system have the same resonance. But now let's look at how waves move in space. Okay, so waveguides. If you have two waveguides, one has gain, one has loss, they are coupled to each other. You need to couple two systems, right, to have the exceptional point. In that case, we look at the wave number of the system. So when you look at waves moving, the wave number is what describes a phase propagation along the coupled waveguide. In that case, the exceptional point happens when you look at the wave numbers. So the eigenvalues are the wave numbers. So when you have an exceptional point, it means that you have two modes that actually become one. They have the same polarization states and they have the same wave number. So you can do it in various ways, okay? I don't know how many people here works on waveguides, but look, the math is identical. Instead of looking at derivative in time, we look, what happens?
Degeneracy.
Degeneracy
of the projector. You can continue. Everybody on Zoom.
Oh, okay.
The people, we just can't see.
Yeah, okay, so
Projector.
doesn't matter if you can see it. So before the derivative was in time, we were following how the system evolves in time. But here it's the same thing. We look how the system evolves quoted in space. But so the math is identical, okay? Is it going to, okay.
Yeah.
So look at this equation. It's basically the same thing, right? Just if z becomes t, it's the same equation. So the math is identical. The physics is different, however, okay? So we look at that. Now I'll show you a little more of math, okay? Before I skip it. So we build this eigenvalue problem. K is a wave number. C is eigenvector, which is polarization states. So if we couple two waveguides, each waveguide has two solutions, a wave moving toward the right, a wave moving toward the left. So when you have two waveguides, you have four solutions, two waves moving toward the right, two waves moving toward the left. So M will be 4 by 4, and the state vector is 4-dimensional. So these are the four eigenvectors, it's graphical representation in 2D of 4 in the 4-dimensional space. So you have 4 independent eigenvectors usually, right? And this is how you describe the state of a system with these 4 ones. Can then become 1? 4 of them now. Yes, of course you can. So we look at these 4 wave numbers, and we want to be sure they become 1. But not just a wave number. This is easy to do. Look, I take two independently coupled uncoupled waveguides. I can have the two wave number of these two waveguides to be equal to each other. Yes, but they are independent. No, here I want them to be coupled. Okay, so I want these polarization states. I want these 4 E and H fields to become the same. Okay, and you can do it. So a little bit of so there are various ways to look at that, right? So here you look at the eigenvectors. This is a system of order 2. You want 2 eigenvectors to become 1. This is a system of order 3. The matrix will be 6 by 6. And you want 3 eigenvectors to become 1. So they become 1 when you change one parameter. And then if you keep changing the parameter, again, this 3 eigenvector split again. Or you can have a system of order 4. It means the matrix, in this case, the matrix is 4 by 4. And these 4 eigenvectors become 1. Well, if you're familiar with algebra, the key point is that at that degenerate condition, the system matrix that I mentioned before becomes similar to a Jordan block. So matrices, square matrices can be divided in 2 classes. Those can be diagonalized. Hermitian matrices are just a particular class. And those that cannot be diagonalized. But the exceptional points happens when the matrix cannot be diagonalized. Okay. So the geometric multiplicity is different from algebraic multiplicity. Okay, so you can look at various different. You can look at the exceptional points from different points of view. Now you can also look at something else. Look at the polarization state, the field. It happens that if you have an exceptional point of order 2, the field not only changes phase like that, but grows linearly with z. If you have an exceptional point of order 3, the field grows with the square value of z. If the system is, the degeneracy is of order 4, you have a cubic algebraic growth, besides exponential variation. If you build a dispersion diagram, when you describe a mode propagation in waveguide, you look at the dispersion diagram, frequency versus wave number. This is standard band gap. If you look at crystals, okay, every crystal is a periodic structure, and if you look at propagation of light in crystals, it's full of band edges. For these frequencies, light is allowed to propagate. This is called the pass band, and below there is no mode. Below there would support propagation, and you are in the band gap. So the band edge is actually an exceptional point. People didn't know that. So people have been dealing with people have been observing exceptional points, but people didn't study the physics really associated to those points. That's the key point. When you have an exceptional point of order 3, you have this. exceptional point of order 4, you have this. Look how flat it is. Look how you approximate your dispersion diagram around this point. Here you have a factor of 4. It means that frequency variation is extremely absent, almost absent near the exceptional point. So this is a third order. To have a third order in a reciprocal system, you need 3 transmission lines, 3 waveguides. So when you change frequency and you observe the wave number is complex, you can see that actually they meet at that point. If I keep increasing frequency, not shown in the plot, they will keep the trajectories. Okay, so you can see what happens near an exceptional point. These 3 angles, 120 degrees, are very important. Why? Because it's related to the cubic root. When you do a cubic root of a number, the 3 solutions are always separated by 120 degrees. And this is a degeneracy of order 4. When I approach this, I see 4 solutions coming like that. These are propagating waves, this blue curve, but you have 2 evanescent waves that actually are going to merge there as well, 2 evanescent modes. We actually did a first experimental verification of microstrips of exceptional point in waveguides. This was the first, and then we did this, and then we did this. Okay, so this was critics were saying, well, how can you be sure you can do it in practice? Everything is so sensitive, and maybe you cannot really realize it in practice. But actually, that's what we wanted to do, experimental verification, to show that it's not just an academic topic, it's something that you can build. I divide the exceptional point in waveguides in 2 classes. Those with gain and loss. You have one waveguide that has losses, one waveguide has gain. And this was 99.99% of the people were studying PT symmetry. And waveguide without loss and without gain. I've been the one studying them here. At the beginning, when I was telling the story, even the famous expert in exceptional point following PT symmetry, they were saying, no, it's not possible. Why? Because the system has to be non-Hermitian. Here, there are no losses. How can you have an exceptional point? Well, actually, you can have an exceptional point, and these are various geometries where we have found exceptional points. The work, actually, for me, the inspiring work was the one by Professor Figotti, a mathematician at UCI, and Dr. Vitebsky, who is a physicist, now working with the Air Force Research Lab. They were studying these ideal crystals made of, parallel layers. So you can have it actually. Let me skip a few slides. Maybe I want to skip this. This is an electrical engineering way to describe things. Anyway, the main message is these are transmission line describing propagation. It's a various configuration, how to get an exceptional point. So if you have a waveguide that has wave in one direction, and then makes it couple it to another waveguide that has waves, a backward wave, the famous mathematical backward wave in the other direction, this is one possibility to have an exceptional point. Okay, and that is represented by this, would be this case. But there are many, many combinations to have exceptional point. That's why we have studied them. Okay, and we did the experimental verification. This is a microstrip strip, and these are just capacitors. And here we showed, look how actually the measurement is so close to the simulation. It's impressive. Okay, this was done by extremely bright student. Okay, who are actually consider interesting ways to calibrate the measurement. Okay, and with another student, here another. This was the first ever experimental demonstration of an exceptional point of order 3, coupling 3 waveguides. Okay, we also invented these coalescent parameters, which is a hyperdistance in the multidimensional space, where we have, for example, we look at the eigenvectors and we measure the angles between these. These are vectors in 6-dimensional space. We look at these angles, and then we build this distance, looking at the distance between these vectors in this multidimensional space. And when we have 3 coalescing, it means that the distance between these three is actually equal to 0. That's what we test here. And you can see this parameter that goes down is a linear scale. This was also obtained from measurement. How you get it from measurement? That's beautiful, right? You get these complex vectors thanks to measurement. Okay, that was it was very complicated. Anyway, so it's not just computation, you can also do measurements about this. Now I'm going to describe how these affect also propagation of optical waves in optical waveguides. This was one of the early papers on the subject. These are a professor in Ohio State University. The key connection is that he was working with people at Ohio State University who had a Munich project together with this mathematician at UCI. And so the idea transferred to them, and these guys started to make silicon-based waveguides. And he was, I don't know if he was able to show it with confidence or was just getting close, but this is an experimental demonstration of getting very close to an exceptional point of order 4 in a lossless, gainless waveguide. These are photonic crystal waveguides, and we came up with another idea. This is a CRO. A CRO means couple ring optical. Ring optical waveguide. So here there are many rings. These are silicon-rich waveguides that are coupled together. And now the CRO was mainly studied by a professor in Caltech many years ago. Now we couple them to another line next to it. So if you take a cross-section like that, here, you can see we actually have 3 waveguides, right? You count 3 waveguides, so the signal can move toward the left or toward the right using 3 waveguides. And then we couple them. We couple them here, we couple them here. So this was a strategy to have exceptional points. And here we show the one of 4th order, which is called degenerate edge. And this is the quality factor. I'm not sure how many of you know the concept of a quality factor, but if you make a cavity, in this case, you make a resonator taking a waveguide, and then the waveguide is of finite length. So this by itself is a cavity. And then you look at the quality factor, and you can see that when the cavity becomes longer and longer, the quality factor usually increases. If in the famous Fabry-Perot cavity, many of you know the name Fabry-Perot cavity. If I take the Fabry-Perot cavity longer and longer and longer, the quality factor grows linearly with the length of a cavity. If I look at the regular band edge, which is an exceptional point of order 2, the quality factor grows with cubic law of the length. This is the number of rings. This was already discovered in the 90s during the early years of slow light. But if you do a cavity with a Degener band edge, the quality factor grows with the power of 5. So it's a kind of different physics. Okay, so you are not optimizing it, you're changing the physics, how the quality factor law changes with the length of a cavity. Okay, that's why it's something big behind it. And we propose this concept of the Degener band edge laser. It was the first time it was proposed in this paper. And if I look at the threshold of this laser, I skip details. We did an FDTD, time domain, discretization of all the equations, including the rate equations that are the base of the laser theory. And we calculate the threshold, and we see that if we increase the length of the cavity of the laser, here we compare 3 cases. This is standard Fabry-Perot cavity, which is a waveguide of finite length L, and we increase L, you can see the threshold decreases linearly, as 1 over the length. And then if we have the regular band edge or the Degener band edge, this is what we care about, you have a threshold of your laser that decays with this power. So there is some new physics here behind that, okay? And then if you look at here, this is a laser, so the nonlinearity is actually important in the simulation. We see how clean is a single lasing frequency of this laser. Okay? How many of you are familiar with the distributed feedback laser, which is the most important laser in these days? I mean, the most common, not the most common. It's mainly based on the grating. Actually, the distributed feedback laser works at this point where you have two modes, one with positive group velocity, one with negative group velocity, and so you create some kind of distributed feedback at any point of the laser. But now we want to do something else. We take two gratings, we shift them a little bit because we need to break symmetry. You need to break symmetry to have a higher degeneracy. And now we have a degeneracy of the red curve. So this is a flat, super flat curve. Remember the degenerate band edge. So our goal is to make a degenerate version of a degenerate feedback laser. The other RF applications, now I'm just going to talk a little bit about applications to tell you that I like the theory. I have been working mainly with the theory, but which I didn't show much about it. But time is limited. But I want to show you that this is actually very useful. I've shown you one application about sensing. Okay. Now I'm going to show you some examples of oscillators. So this is a cavity. This is a microstrip waveguide. We have two couple microstrip. Below you have a ground plane. This is in periodic coupling. By the way, you see the broken symmetry. You need to break the symmetry to have an exceptional point. And now we make a cavity, and then we put an active component here that provides some gain. And then the system becomes unstable. The signal grows, it saturates, and then this is the saturated regime that you see a clean single frequency of oscillation. Okay. Look, you have 10 dB per division. Look how clean is this oscillation frequency with respect to the noise. I mean, it's a very, very clean oscillation frequency. Okay. Okay. Another interesting aspect of this exceptional point. So let's assume you have a conventional fibrillar cavity. What happens in a fibrillar cavity? You have your resonant modes. This is a cavity like that. Usually the electric field peaks at the center, and then it's minimum at the edges. What happens to the magnetic field? Peaks at the two edges, and then is minimum at the center. So if you plot the energy distribution inside the cavity, it's flat. Okay. Now, what happens if you have an exceptional point, like those degeneracy conditions, and you look at the energy, not at the electric field energy, the total energy distribution? It happens that it's concentrated at the center of the cavity and goes to zero at the edges. And even if I take this microstrip, this waveguide, I continue it without interruption, you don't change the structure, the distribution of energy. So it's incredible. So you can continue these waveguides without the coupling, and then this is still a cavity. So you don't need to put mirrors to build these cavities. That's a beautiful thing. Okay. So look, we want to use it. This was the oscillator I had before. This is injecting power in the system. I'm making an oscillator. The energy is going to be is going to peak at the center. Okay. And then what happens after I put the energy in the system? Well, let's put a switch and the load there. When I close the switch periodically, then I create pulses. And this is very short pulses because the energy is all at the center of the cavity. I don't need to wait that the energy of the whole cavity gets out. I just take energy that is at the center and immediately goes out, and then there is no energy anymore. You can see how these pulses are sharp. Okay. Another idea based on the physics of exceptional points. Oh, this is the beauty. Okay, this is, in my opinion, the other great application. I would like to work with people expert on nonlinear models to develop this. So what about active integrated arrays? So you take a various oscillators, you couple them, and there's a little bit of coupling. and through injection locking, these oscillators tend to synchronize to each other. But what about if I have this oscillator, the phase that is reaching this one is different than the phase that is reaching this. So you can have injection locking, couple different oscillators, but eventually the phase coherence is going to fade away because you try to couple very distant oscillators. Okay, so that's a limitation. If you solve this problem, you're going to have a large system that can radiate, and all these elements are fully synchronized. So you can generate a lot of radiated power, very monochromatic. Okay. So this is what we did. At the moment, we just do some simulations, but there are still a lot of things we don't understand. So these are gain elements. It would be a biasing line. This would be a waveguide. We put various antennas, which are just losses. We let the system oscillate, it's unstable. And guess what? It oscillates at the exceptional point. So of course, we build to have an exceptional point. We make it unstable, and the system naturally oscillates at the exceptional point. And this is always the case we have observed. Of course, because of nonlinearity, you have harmonics, but we don't care about that, okay? That's great. However, this exceptional point was designed that all these elements are in phase. What happened is that actually out of phase, 180 degrees. So instead of having an exceptional point at k equals 0, we have an exceptional point at the edge of a Brillouin zone. Remember, it's a periodic system, so you have the spectrum that is repeated. You have a Brillouin zone, and so how is it possible? We spent months and months and months to understand. We discovered that there is another exceptional point associated at the edge of a Brillouin zone. So interesting, because of the nonlinear dynamics, the system moved away from an exceptional point and it ended up at working at another exceptional point. Amazing. So exceptional points are these attractors that when systems tend to work at their region. Now, if you make this exceptional point exist with G that is significant, this could be a very high power radiator with all elements super synchronized. Why are they synchronized? Because I'm not just waiting that they synchronize inside the cavity. This is much bigger, much stronger than a cavity. We have this internal high degeneracy condition. In this case, the degeneracy over there too, but you can build also 3, 4. So this degeneracy condition is making all these different oscillators to be strongly coupled. So we do the other way. We try to couple them as much as possible. Okay, this is another example. This would be an active liquid wave antenna. Liquid wave antenna is a radiator. It's an antenna, so it's a distributed radiator. And then there is another transmission line which is active. So the become an active antenna that oscillates and radiates. And this is a key point why it's interesting, because if the liquid wave antenna works at the exceptional point, we just need to change a little bit of a coupling, and then we have a big change in the radiation. Either the radiation is moving immediately to another direction, or the beam becomes much bigger. So this is a good idea for a sensor when you want to sense through radiation. An example, a spectrometer. Take a Raman spectrometer, they have to be very precise. Usually it's a grating, you have an incident field or the guided, and then all the colors are spread, and then you have CCC the camera, and each camera basically will tell you the frequency produced by nonlinear spectroscopy. The bigger this spread you have of colors, frequencies, the better, right? The more sensitive it is. Oh. So I'm done. I just want to say the last thing, we have been applying this to electron beam devices. I don't know if some of you is working with electron beam devices. It's a big topic for me. We try to work with traveling wave tubes. So we have an electron beam, we couple them to a waveguide, and so we couple electromagnetic waves to waves in the plasma. Through synchronization, we have amplifier or oscillator. We introduced the concept of exceptional point, and we got extremely a lot of benefit. Okay. just to give you an idea. With exceptional point, we get an output of 3 kilowatts. Without exceptional point, we have 200 watts. With exceptional point, we have an efficiency of 20%, which is super high in millimeter wave. Without exceptional point, you have an efficiency of 1%. Okay, so it's a huge difference. So here we see it's one of them. This is not typical. To make these outputs along the transmission line is not typical. So we need to convince the people that work here in this technology that is working. But really, the efficiency of these devices at millimeter waves is very small, just a few percent. Okay. So I stop here, and thank you.
Okay. Any question? I think it was very, what you can say, energetic and illuminating talk in terms of the topic, and I have to learn a lot. I'm a more experimental person, so this is something I have to learn also before I can ask myself a good question. So if you all have any question, those who are from physics, math background or any electrical engineering background, please ask a question.
Yeah,
yes.
Curious actually, fairly new for me. I'm working in the coastal engineering as we were talking before. For example, there is a typical problem in which you have an internal wave, coastal region and the ocean, which you have a wave which is internal, and you have another wave which is a surface wave, the typical wave.
Internally means at the depth.
Yeah, because you have a change of density and the interface.
And they can be coupled, of course.
And you can have a.
These are two waves, they can couple to each other.
Exactly. And I'm thinking that maybe you can reach an exceptional point because you have, if both are sufficiently significant, they can be coupled and one can affect the other and the other can affect the other one. So you can get an exceptional.
Yeah, and when you have an exceptional point, it means that they're not just waves that will move with different velocity. It means they start moving with the same velocity. And we will see also a growth in amplitude.
That is my question. So if I'm working with hazards, I don't want to have a wave or a.
Yeah, but it would be interesting to study if it is possible.
Because if you reach the exceptional point,
of course, we'll be back.
in trouble. You will have huge waves.
But yeah, but they're not toward the coast, right? They are along the coast, but
Yes,
still can be
they
dangerous.
are propagating.
Excellent. I mean, can you model these waves? You have an analytical model.
That is the problem because typically, well, Ricardo, we were talking about a little bit about nonlinear waves. But typically when we deal with internal waves, or at least how I address that problem in my courses when I was taking those courses, it's just completely isolated, linear. When you are working with the internal waves, you are assuming that you have a flat surface, actually, or at least that is how I studied.
Yeah, but can you study the coupling between these two waves? Numerically, you can.
Certainly, there are.
What about analytically? Can you study also the coupling?
There are some canonical solutions, some problems which you can actually investigate. Certainly.
Yeah, but there is definitely a way to look at that. Now, even from numerics, I can recognize that there is, if you're close, if you're far away from an exceptional point, okay? If you show me a bunch of simulation moving something, I can see if you can get there. But that system has losses, right?
Yeah.
So the losses will give you an exponential damping.
Exactly. Yeah.
But actually, waves is self-sustained because there's some extra energy coming into the system somewhere, right?
Exactly.
So it's a complicated problem. But yeah, I think there could be. Yeah.
Yeah, no, I'm curious because it's the first time I hear about exceptional point. So,
Well, I never thought about this application, but I think yeah, it could be one case where you can find that.
But numerically, you can also couple the two.
yeah, numerically, like Peter and Cornell can make that kind of thing.
Any other question? Yes, please. Yes.
Very nice talk.
Thank you.
I have a question on your harmonic oscillator LC
Yeah.
with the EPDs and how you can interface with the qubits, for quantum application, quantum sensing, let's say, for superconducting qubits with your harmonic oscillator, how EPDs are going to play any role there.
I'm thinking about it. Yeah, I don't know. I'm thinking about it. I think it depends what you want to do. Okay, so if you want to use it for sensing or for communication, what do you want to do?
For networking, for communication.
Yeah, I'm not. I don't know. I don't have an answer for that. I mean, I'm not saying no, but I'm trying to think about that. Okay, but I haven't reached any conclusion. Yeah, but definitely you can have this in quantum systems. Is actually what I'm trying to do. To have a quantum system that is very, very sensitive thanks to an exception point. How do you do it? For example, by time modulation. If I time modulate the quantum system can be a single atom or a bunch of atoms. Okay, so and then we look at what happens, and we'll be more sensitive if you're able to, with time modulation, to synchronize your system to work at exception point. So that's the application we're looking at.
Yes. So with respect to applications, one of the nice things about these exceptional points is what you mentioned about the eigenvalues having these square roots.
Yeah.
But that relies on you knowing exactly what the bifurcation point is. So forget about perturbations of your state. You will have perturbation of your parameters of the system. So
indeed, here I just represent, I show the perturbation of the eigenvalue. Eigenvectors also undergo analogous perturbation. Eigenvectors too are perturbed according to the square root.
Right. But the question is, you need to know where the bifurcation point is, because all these very big slope relies on you knowing perfectly where that bifurcation point is.
Yes.
So if your system is not parametrically stable, meaning that changes in the parameters will also change where the bifurcation point is, then you're going to lose all sensitivity because you don't know. So it's like a cat and mouse or chicken and the egg. Yeah, you are very precise. You're very precise if you know where the bifurcation is, but if you don't know where the bifurcation is, then you're going to be the opposite of precise because it's going to actually shift your value left and right.
Yeah.
So how do you deal with these kind of parametric instabilities or parametric sensitivities in practical applications?
Well, it's a big question. I mean, I don't know, but you know, we see that sometimes it depends. Sometimes the perturbation just shifts. If you perturb the system, sometimes you just shift the exceptional point. Sometimes you destroy it. So let's assume you destroy it. You want to reconstruct it. You need to have a feedback mechanism that is looking at the observable of your system, not the eigenvalue, but even the eigenvectors. And then you try to make it converge looking, that's why we invented this coalescent parameter. So that's what we use almost all the time. We want to make an exceptional point in a system. One way we have the same problem. We have a system, we don't know what the exceptional point is. Then we do simulation, and then we do another one. We see how this is a cost function, basically, this coalescent parameter. So we have we build an optimization method, and then we find the exceptional point. We find the values that will give you the exceptional point. So you could do something like that, automatic with the feedback mechanism.
Yeah, but then if your system is not stationary, there are temperature variations or vibrations in the analytical system, you cannot actually assume that the exceptional point that you computed a half a minute ago is still at the same place. So you will basically kill all the sensitivity, unless you have some sort of feedback.
Yeah, exactly. So you need to recalibrate the system constantly. So if your system is very sensitive to temperature, and you want to measure temperature, that's difficult because you need to find it, and then the drift of your system has to be slower than what you want to measure. But if your system is sensitive to temperature, you want to measure pressure, or people do it, for example, in gyroscopes, accelerometers, you know, these are applications of sensors. That is different than temperature, so you can calibrate the system because you're looking at something else than temperature. Okay, so that case is easier. But we haven't worked on that, but yeah, something that should be implemented.
Good, thank you. So can we ask question if any virtual attendees have a question?
There's nothing in the chat right
Okay, so if any other further question from the attendees here? If not, let's thank the speaker. Thank you very much.